Okay, so let's continue on with the momentum chapter. So let me just recap what we were doing. Defined linear momentum. So momentum is mv and has a relationship with the force in this way, according to like the time derivative of the momentum is actually equal to the force, basically because F equals ma. And we can also define momentum for a system of particles, just add up the individual momenta, but this has a nice interpretation of actually being maybe I need to, if I ask you to be more person. Yep, thanks. It has a nice interpretation in terms of the motion of the center of mass. So we can either view this as just the total momentum, or we can view it as the center of mass and how that's moving. The velocity of the center of mass is something like over here, sorry. So the total momentum is equal to the mass, total mass times the velocity of the center of mass. So that's, you view it as a composite object, or you view it as individual particles. So why define this thing? Well, we're going to come up to it, which is basically conservation of momentum, which I think many of you probably heard of already, but it does have a nice mathematical kind of definition in terms of, you can view it in terms of the center of mass and take the time derivative, you get something like a momentum quantity, and take another time derivative and you have a total force. And we got up to somewhere around here where we're talking about so-called impulse. I don't particularly like this term impulse. It's just, seems like bringing in another term, which is, essentially it really is just change in momentum. So if you invert that relation of the derivative of the momentum is equal to the force, so of course if you integrate that equation, then you'll get the integral of the force is equal to the momentum, right? And for some reason we call it impulse, but it's really just how much the momentum changes. And if you look at, say, a force applied on a ball here, and that how it moves, then if you integrate that with time, that is also how much momentum you give the object. So I think that's where we got up to last time. So let's just do this question quickly. So a paratrooper whose parachute fails to open, lands in snow. He's hurt slightly. He had landed on bare ground. Stopping time would have been 10 times shorter, and the collision lethal. Does the presence of the snow increase, decrease, or leave unchanged the properties of the paratrooper's change in momentum? Is that the same? Like, is it increase, decrease, or unchanged?
Speed is the same, right? So
yeah, unchanged. That's right. Yes. So basically, what's happening is that he's going from some velocity to a stop, right? So there's a change in momentum of mv final minus mv initial. This is wrong one. This is 0, so, minus mvi if you like. So that is the same regardless of if he's landing in snow or if he's landing on concrete. So impulse stopping the paratrooper. The impulse which is change in momentum. Is that increase, decrease, or the same?
Time is shorter on the ground. Oh, you say the snow increase?
Well, the second question is talking about impulse.
Okay.
Yeah. So we'll get to the point that you're trying to make there in the next part, I think.
It's just change of moment.
Yes. This impulse is just change in momentum, really. So I think what it's getting at is actually, it's talking about the force that's maybe applied by the ground. So here's the guy, let's say he's going down with some velocity here, and in order for him to be stopped, there is some force in the opposite direction, obviously, to slow him down, right? Because eventually he's going to come to a stop. So the impulse is integral of ft, and well, we know that eventually that's just equal to the change in momentum anyway, right? And then we already said that the change in momentum is going to be the same on the snow or if it's on hard ground. So basically the impulse is going to be the same because impulse is basically change in momentum. Okay, and then finally, what about the force stopping the paratrooper? Is it decrease, in the presence of snow, increase, decrease, or leave unchanged the force?
Decrease.
Yeah, decrease, yes. So, we could say, for example, roughly speaking, this is force times the whatever time it takes to stop him, right? And so if he's on some kind of snow like this, then the force can be, you can spread it out if you like, right, over time. And so, as he's crashing through the snow, there's a smaller force, but it's for a longer time. So that's how the total momentum change is going to be the same as if he was crashing on hard ground, where basically all that force has to be kind of applied all at once as he's just hitting the ground.
I think rigorously should be the average of
Yeah, okay, yes. I mean, if you looked at the force,
Can I compare the functions?
yeah, exactly. So, it'll probably look something more like this. This is the snow version, and then this is on hard ground,
Yeah.
something like this, right? So, yeah, that's right. Okay, so this idea of an average force, so exactly what we're saying here kind of ties in with what this slide here is talking about, because here we have, if we've got a series of collisions, say you've got this situation where you've got this object here, and you got, say, like a BB gun, and it's like sending in like these balls, but it's continuous, right? So it's going tick, 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 hitting the side of the wall of this object. And you can imagine that, if it's kind of fast enough, it's actually providing a average force on this object, right? Because it's just happening kind of all the time. It's just hitting the side of this target all the time. So if you look at the force versus time graph, it would kind of look like this. For each ball that it's hitting the side, there'll be like a force spike. But we can kind of talk about and say what's the average kind of force if you sort of think of all these balls hitting it very fast. you can kind of consider what the average force of this whole thing, from the point of view of the target, what the average force is. And essentially what you're trying to do here is you are, instead of looking at a forced versus time graph that is sort of, going up and down like this, we're kind of flattening out this whole curve because this impulse is essentially the area under the curve here, right? So that, maybe I should have written J here. So the impulse is just how much, the area under the curve, and this is basically equal to the change in momentum. So we can, using this idea of this impulse, we can work out what an average force is, and so the argument would go something like this. So first we'd calculate like the total impulse, which is the area under the graph of all these things here, right? And then what we're trying to do basically is to kind of, flatten this thing out so it's just square and has like a constant force profile rather than something which is spiked like this. So first we can work out what the total impulse here is. Of course, we can do this by calculating the area under the graph of each one of these. So let me just redraw this. So here's the force profile. Each one of these are the same, so draw this a bit better. And let's look at like what's the impulse of like one of these. So of course you could just integrate this thing with time, but it's actually easier just to look at the change in momentum of the particles, because what we know is that from Newton's third law, right, that the force on these balls is actually going to be the same as the force on the target, right? So this is really talking about the force as experienced by the target, right? So I'm really talking about this force here, right? But then there's also of course, a force on this ball, which is equal and opposite, right? So this is a force on the ball that's going to do like this, go like this. And basically what that's going to do is to change the momentum of this ball, right? So there's going to be some change in momentum of this ball, which is, mv final. Well, let's just call it, follow the mass times the change in velocity of this ball. So we could actually just work out what the area under this graph is, not by actually just integrating this graph, which might be kind of a complicated exercise, but we can get it in a much simpler way, which is just to look at the change in momentum. And then all we've got to do is just measure the change in the velocity of these balls here. So say they're coming in with some velocity. Suppose they, say they bounce right off the wall, right? So say the initial velocity is v, and then it comes out, and then it's minus v. In that case, it will be, the change in momentum will be like 2 mv, right? So for example, if Vf is equal to, so this way is minus v, Vi is plus v, then the change in momentum might be 2 mv, of medical is v0, just so it's confusing. Might be something like this. Okay, so that's the impulse of one of these spikes. Now we just have to take into account the fact that that's happening every some time, right? Okay, so every some number of seconds that's happening. So basically we just have to multiply by how many spikes there are, right? So the J total would be basically the number of these balls hitting the object in a particular time. Yeah. And okay, yeah. And the reason why there's a minus sign here is because right. Okay, so sorry. I think I needed a minus sign here because this force on the object is actually the minus of the force on the thing here. So sorry, I needed a minus sign here. And notice that this one, sorry, I think I also needed a minus sign here because delta P is the final momentum minus the initial, right? So this is minus V0 and this is plus, so it'd be like minus MV0 minus MV0, right? So it's actually, this is a negative quantity, basically because but the ball experiences the opposite momentum change to the target, but we're talking about the target. Okay, so sorry, I needed a minus sign here. And oh, sorry, that's already the expression here. So okay, sorry, no, the average. Oh, okay, sorry, I think I've got my variables mixed up. So n is n is the, okay, what is the definition of n here? N should be the okay, so mess this up slightly. So I believe it should be like this. And then the definition of n should be the right, okay, so yeah. So we need to say like say you've got some n should be what? Should be the number of balls hitting the object per unit time, right? Okay, so the delta T, I believe, yes, and this is what happens when you don't define the things properly. I didn't put my definitions on the screen. So I believe that delta T should be defined according to the that number not saying okay, so I think it should be number of balls that are hitting in a particular time, right? T, and then yeah. So if we're looking at interval T, So look at some interval t, and then this is the number of balls that hit it in that interval t. And so that's the total impulse that's given to the object. And then the F average should be, well, okay. So the J total should also be equal to the F average divided times by T. And so the F average should be just the J total divided by the time. And so this is N delta V T. And so I think this N over T should be basically the number of balls that's hitting it per unit time. So, okay, I'll clean up the notations here later on. Okay. All right. Okay, so let's try this question. So the figure shows an overhead view of the ball bouncing from a vertical wall without any change in speed. Consider the change momentum in the ball's linear momentum is delta px positive, negative, or zero.
The momentum as the speed up.
Yes, so the px, this is the momentum, it's going at some angle, so x is just in this direction. So this one, because cosine of this, the x component of this will be the same over here and here because the velocity is the same, so this will be unchanged. What about delta py? Yes, so the final velocity is positive and the initial velocity is negative, so this would make the change in momentum positive. And what's the direction of the delta p? Yes, yeah, exactly, yeah. So the the change in momentum is actually straight up. This also basically tells you that the force that's applied on the object is straight up, as you can sort of probably guess just from the geometry here. So it's perpendicular to this surface. Okay. And then we finally get to the conservation of linear momentum, which is the main sort of result of this chapter. This is just the definition of the total momentum. And if you have a particular case of this where the momentum is actually there's no external forces acting on the system, then this left-hand side of the equation is zero, and then if you integrate this, then you will see that this total momentum is actually a constant. And if it's a constant, then that means that these particles might interact with each other, but then at the initial point and the final point, the momentum will be unchanged, meaning it's conserved. Right? So if you look at the total momentum of these guys some time before and look at total momentum after, then the momentum doesn't really change. Okay, so you know, this is a very useful relation to work out the you know, velocities or some quantities of for a system, but you have to keep in mind that it's only for when there's no forces or no external forces. These things can like collide with each other. That would be completely fine because these are internal forces. But if there's any external force, you can't apply this conservation of momentum because that's it's not an isolated system. Okay, so just a few sort of things that need to be careful. I've already mentioned, I think, one of them. But so the first one is that this is a vector equation, so you can apply it in the x and the y and the z directions separately, and it will hold separately. As I said, only applies if the net force is zero. Can't just always apply it, actually. And somehow it's a stronger sort of relation, or it's a relation which actually holds a little bit more more often, if you like, than say conservation of energy. You know, there are many cases where you have conservation of momentum, but not conservation of, say, mechanical energy, and this is basically because the energy tends to easily leak out into other forms. So if you've got you know, two colliding balls, you know, some of that energy would be turned into sound or heat, things like that. So you might not find that the mechanical energy is exactly conserved, but momentum somehow is kind of better conserved. And I think this is mainly because you know, there's not other forms of momentum, right? So, you know, energy has many forms. There's thermal energy, there's sound energy, all these other things. But momentum is a kinematical kind of thing. It's like something which really you need to have something moving in order for it to exist. There's no such thing as, like, you know, thermal momentum. Well, you know, actually you can, but you know, if you're colliding two balls, then that momentum can't really escape into other types of momentum very easily. So so somehow it's a bit stronger relation than energy, simply because there's less kind of ways momentum can go into other forms. Okay, so let's try this one. So initially stationary device lying on a frictionless floor explodes into two pieces, which then slides across the floor, one of them in the positive direction. What is the sum of the momenta of the two pieces after the explosion? Yes, yeah. So it's initially stationary. That means the initial momentum, the total system is zero. So the sum of the two pieces' momentum has to be zero. And the second piece move at an angle to the x-axis?
No.
Yeah, no, because one of them goes in the positive direction. So x, y. So initially it's here, and then this piece goes that way. Basically, there's no way for this other piece to go any other direction than this way, because that's the only way these two momentum vectors, so this is one, this is two, these two momentum vectors can combine to become zero. Right? What's the direction and the momentum of the second piece? Well, I guess I've already drawn it. So it's in the minus x direction. Okay, and so, yeah.
I don't get why is it zero momentum?
Because, okay, so initially stationary device, right? So this is the final configuration. The initial configuration was like this, right? This thing breaks into two pieces and then flies across. So if you look at this, well, if you calculate the total momentum of this object here, so say this piece was m1, this piece was m2, right? The mass of this thing would be m1 plus m2. And initially stationary means that the mass of the initial piece is zero, right? And then, so the total initial momentum is mb, which is zero vector even. Yeah. Okay. Okay, so now we can talk about elastic, inelastic collisions, and basically elastic, inelastic are just words to mean whether energy is conserved or not conserved. So elastic means energy is conserved, and inelastic means, well, energy is not conserved because of the reasons I said before, like it goes into other forms of energy, thermal energy, sound energy. So a sort of an extreme, well, a particular example is, say this is like a clay ball and it collides with this one, then it deforms so much that it's the energy of the system is, the mechanical energy of the system is not conserved. So so in inelastic collisions, because only momentum is conserved, basically if you wanted to work out what some variable, say final velocity is, then the only thing that you can use is the conservation of momentum equation. So you've got two bodies, m1, m2, two velocities, and then we know that the final momentum are the same here. The classic kind of question that you might have is, say you know the two initial velocities and then maybe one of the final velocities, then using this equation you can work out the final velocity of the other system. So, you've got one equation with one unknown of one of these velocities. Special case is so-called completely inelastic collisions. So this is a case where the final object kind of sticks together, a bit like that clay ball example. So if the final system, the two systems stick together, then the final velocity is actually the same for the two objects here, right? So the V1 final and V2 final are the same. So we can just call it V, big V. And in this case, we can work out what this final V is if we know what the initial velocities are just by rearranging the conservation momentum equation. Just put this on the other side here. Oh, okay, sorry, no. This one is also considering the special case of this one's initial velocity is zero. So sorry, yeah. So more generally, this completely, I think, inelastic collisions be like this. But if you have this case where the initial velocity of one of the systems is zero, then then it becomes this, because this one is 0 here. You just rearrange this equation, m1 plus m2 is on the bottom, and yeah, get that. Okay. If you look at the center of mass of the system in a completely inelastic collision, it's a little bit like that billiard ball example which I had a picture of earlier on. So in a collision, when two, say, billiard balls collide, actually the center of mass of those two systems, there's no change actually in the direction. It's just along a straight line. So it's also the case with this one. If you have a object which is initially moving, and here's one where the initial velocity is 0. Now, if you track the center of mass of these two things, it will look sort of something like this. This one's not moving, so this one's just getting closer to it. Now, after the collision, it sticks together, right? So obviously the center of mass after it sticks together is in that position, of the combined two balls, right? So, so we can work out that the velocity of the center of mass is actually just again using this equation where if we've got the momenta of the individual particles, then if we divide by the total mass here, then it's the velocity of the center of mass is equal to this. Okay, so body 1 and body 2 are in a completely inelastic one-dimensional collision. What is their final momenta if their initial momenta are respectively 10 and 0? Okay, so maybe we should I'll just go through it with you for this one. It's a completely inelastic collision, right? So we go M1, B1 initial, M2, B2 initial, M1, B. So I'm just going to start with the general conservation of momentum. And basically, for completely inelastic collisions, the final velocity is going to be the same for these guys. So let's just put that in. So the fact that it's completely inelastic tells you it's that. And so it's asking what is their final momentum if their initial momenta are 10 and 0. Well, so actually it's only asking final momentum, so not even asking final velocity. So
is it anything to do with incomplete inelastic collision? I think.
Yeah, I guess not really. Yeah.
Yeah, if the conservation.
Yes. Yes.
Yeah.
Yeah. So I think.
Just in sum it up.
So final momentum of the initial momentum. 4. Yeah. Yeah, I think you're right. Yeah, I think it doesn't actually matter that it's completely inelastic.
Yeah.
Yes. Yeah, so it's already telling you the initial momentum. And so, well, yeah. So this is the final momentum of the combined object at the end. So all we have to do is just add them together. So 10 plus 0 is 0, 10 plus 10, 10 plus 0 is 10, 10 plus 4 is 14, and 10 minus 4 is 6, right? Okay, but for elastic collisions, we also have conservation of energy. Kinetic energy, rather, yeah. So we can actually, we have sort of one more equation actually, so that actually gives us more information if we happen to know that it's elastic. If it's inelastic, then we've only got momentum, so we can write down two equations like this. So we've got the conservation of momentum equation, got conservation of kinetic energy, and so we can actually work out what the initial and final, the final velocities for particles 1 and 2 just from the initial velocities. This is not true for the inelastic case because we didn't have this equation here. We only had kind of one equation, right? So we needed to know three out of these 4 variables to work out what one of the velocities is. But in this case, we've got 2 equations, so we can actually work out 2 of the variables, right? Okay, so let's just do that then. So how do we get these equations from these ones? So let's start with the kinetic energy equation first. So this one says half m1 v1 initial is half m2 v2 initial. Final like this. I'm going to get rid of these factors of a half already at this point. And then I want to put these ones with the same m1 variables on the same side. This one is going to be V2F, V2I. And then we do a difference of squares. So difference of squares you can factorize like that. Okay. We can also, so let's call that sort of equation 1. We can also kind of rearrange the momentum equation so that it looks a bit similar. So I'm going to put the M1s on the same side. So this one is going to be 1I minus 1F. I just put this guy on this side and this one on that side. Okay, so this is that equation 2, and so you notice that this thing here is actually the same. Also, this thing here is the same as there. So if you do something like equation 1 divided by equation 2, then we get another relation that looks like this. So what we're going to do is to So let's try, and what we're trying to do here is to get an equation for, say, V1F first. So, should we do it here? So, let's start with the momentum equation. So let's so the momentum equation says okay. So M1 V1F should be equal to this one, just from the momentum equation. And we're kind of trying to basically get this equation so that this only involves terms with the initial velocity, right? So let's use equation 3 to eliminate this one here, because V2F should be equal to V1I plus V1F minus V2I. Oh, wait a minute. Oh yes, right. So we're going to have to factorize this V1F here. Okay. Okay. And then let's put this V1F on this side. So we're going to have M1 V1F, M2 V2F. Okay, so counted for that one. We've got a M1, we've got a VI, V1I here, so M1 minus M2 V1I. So accounted for that one and that one. And we've got a M2 V2I here. Oh, this one is going to be 2 M2 V2I. Okay, and then we can factorize this one. This side, sorry, I think I've just written the wrong thing here, right? This one came from over here, so M2 V1F. So V1F is equal to this stuff here, then just putting this on the denominator. So that's how you get that. So it's a little bit of tedious algebra, I suppose. but we can get that V2F equation. There's just a simple way to get that without doing all this again. V2F. I think the simplest way to get this V2F equation is to relabel 1 to 2, right? So I think if you get the V2F equation, of course, you know, what you call 1 and 2 is kind of up to you, right? So what you can see here is that if you relabel 1 and 2, so if you call 1, 2, and 2, 1, then you'll get this equation, because that's just a relabeling. Okay, so, well, personally, you know, I don't think I would remember that formula. I think that's a little bit too much to remember, but what you just sort of remember is more the principle of, okay, so if it's elastic, then conserves kinetic energy and momentum, and then so you've got two equations to deal with, and so you should be able to work out two variables from that, and the rest, I don't know, I think you'd have to just work it out case by case rather than remembering that particular formula. Okay, so yeah, all right. Okay, so we'll leave it there and see you Tuesday.